Hello everybody. Now we'll start a session on Introduction to Graphs. Graph is one of the nonlinear data structure. This data structure will be useful whenever you want to arrange the data in a hierarchical order. I think in the previous session we have seen how to organize the data in a linear order. Those are all comes under linear data structure, whereas your graphs comes under nonlinear data structure. A graph can be represented in various ways. It is having some set of vertices and set of edges. So from the definition you see a graph G consists of two things. One is number of vertices, second is number of edges. So whenever you want to represent graph, you should have two things. One is vertices and second one is edges. So you can write V is set of nodes and E is set of edges. Edge means what? Edge means the connection between two vertices. So to represent the graph, you have to write like this. See, observe here. G equal to V of E. Okay, that means it is a collection of vertices and edges. So in the definition you can say graph is a collection of vertices and edges. And E is nothing but connectivity between two nodes. So you can write like this: E equal to U comma V. So V is one of the node and U is another node. So both are two different nodes. When you combine both U and V, then that becomes an edge. So while writing, you should write like this: E equal to U comma V. Okay. So U and V are said to be two adjacent nodes or neighbor nodes. So please observe here, U is one of the node and V is another node. When we are combining, then that becomes edge. Edge is generally represented by E. Fine. So when you represent multiple nodes and multiple edges, then the entire thing is known as graph. So if you see this graph, this is edge E1, this is edge E2, and this is edge E3, and this is edge E4, and this is edge E5, and this is edge E6. So you are having multiple edges, and how many vertices are there? 1, 2, 3, 4, 5. 5 vertices. So a graph can be represented by a set of vertices and edges. That's why in the definition you wrote like this: G equal to V comma E. V stands for vertices, E stands for edges. Next, you see the example here. I have given some set of graphs: graph 1, graph 2, and graph 3. In a graph, there is a specialty. What is the specialty? There may be a cycle or there may not be a cycle also. Maybe a cycle or may not have cycle. If you see, cycle means what? When you traverse from a particular point, again at the end you can reach there. Starting point and ending point, when it's same, then that becomes a cycle. So in a cycle, in a graph, there may be a cycle. Please observe here. In the graph 1, the vertices are A, B, C, D, E, F. That means there are 6 vertices. And how many edges? I told you edge is represented by the neighbor nodes. So A and B is one edge. So this is one edge. A and C is another edge. This is here. And B and C, this is another edge here. B and D here. D and E here. And D and F here. And E and F here. And C comma E. C and E also one of the edges. C and E. Okay. So like this you can set a set of edges. Similarly in the graph 2, please observe here. A, B, C, D, E, F. A, B, C, D, E, F. They are all vertices. And edges A, B, is one of the edge. AC is another edge. BD is another edge. CE another edge. CF another edge. Yeah, all are represented here. So this is one. So you can say graph 2 is nothing but the collection of vertices and edges. You can write like this also. In a graph 3 also you can write like this. So in a graph there may be a cycle, there may not be a cycle. Cycle is not compulsory, but there is chance of cycle. If there is no cycle in the graph, then that is also known as a tree. Please remember, when there is no cycle at all, then that is also known as a tree. So here you can say also a tree. So remember here there is another graph 3, A, B, C. A is pointing to B, B is pointing to C, A is pointing to B, and C is pointing to B. A, C, B, and here there is no cycle at all. So it is a simple, of course, graph. At the same time it is tree also. Now the vertices are A, B, C, and edges are AB. AB is one edge, AC is another edge, and CB another edge, C to B. And this graph is called directed graph. This graph is called directed graph. Okay. Where this graph is non-directed graph. The direction is not specified. A graph also you can divide into two types, directed as well as undirected graph. If a graph consists of set of nodes with a particular order and direction is specified, then that graph is called directed graph. If a graph contains ordered pair of vertices and with the direction specified, then that graph is called directed. If an edge is represented using a pair of vertices v1, v2, then the edge is said to be a directed edge from v1 to v2. If the first element of the pair v1 is called start vertex, then the second element pair is called end vertex. So first is starting vertex, second is ending vertex. Okay, or starting node, ending node. Sometimes we'll say node, sometimes we'll say vertex. Both are same. Both are same. If you observe here, the vertices are 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And edges are 1, 3, 1, 5, 2, 1, 2, 3, 2, 4, 3, 4, 5. So you can see this one. 2 to 1. 2 to 1 is there. So this is one edge because the direction is specified like this 2 to 1. But you cannot write 1 to 2. 1 to 2 is not mentioned here. If at all bidirection is given, in that case you can write 1, 2. 1 arrow 2. Okay. So depending upon the direction, you have to write that pair. Now 2 to 3, it indicates what? It is connection from 2 to 3. That means the direct arrow is going from 2 to 3. It is a directed edge. Similarly, 2 to 4. 2 to 4. The arrow mark is specified here. Similarly, 3 to 4. 3 to 4. So 3 to 4. If you write 4, 3, then that is wrong. Because in directed graph, wherever the direction is specified, you have to go in that way. Starting and ending. So here, 4, 3 is wrong. So like this, you can define the set of vertices and edges for a directed graph. If the graph contains unordered pair, if there is no order, there is no direction specified, then the graph is known as undirected graph. So in a graph, a pair of vertices represents the same edge. Same edge. So whether it is 1, 2 or 2, 1, both are same edge. So in undirected graph, 1, 2 or 2, 1, both are same. Whereas in directed graph, both are different. Both are different. In an undirected graph, the nodes are connected by undirected arcs. It is an edge, hence no arrow at all. Here there is no arrow mark. There is no arrow mark. Both the ends of an undirected arc are equivalent. There is no head or tail. There is no starting or ending. Anything can be starting or anything can be ending. So you can write like this. 1, 2, 3, 4, 5, 6. And these are the vertices. Okay. So this is the two categories of graph. One is directed, another is undirected. So you can say directed graph means where direction is specified. Undirected graph means where there is no direction specified. So remember, in the direction graph you will build a arrow mark. In undirected graph there is no arrow mark at all. Now there are some set of terminology you should know in the graph. First is degree of a vertex. It is written as degree of u. It is the number of edges containing u. If degree of u equal to 0, then u does not belong to any edge. Then u is called isolated node. That means, for example, there is a individual node. It is not connected to anywhere. So that means there is no vertices or extra nodes are not connected at all. It is isolated. So here the degree of vertex is 0. Now please observe here. If here for this A, the degree is 2, because from A to B as well as A to degree, A to D. So here the degree of A is 2. When you come to B, degree of B is, it is connected to here, it is connected here as well here. So degree is 3. So the number of connectivity will be known from the degree of vertex. A path, next word is path. A path P of a length n from a node u to v defined as a sequence of n plus 1 nodes. So you can traverse the graph from starting to ending with different routes. So in the path you can specify from where you are starting and from to where you are reaching via which nodes. So v0, v1, v2 up to vn you can specify n number of nodes. Whenever starting and ending both are same, then that become a cyclic path. Okay. Path from A to D is A to D, A to D and here. So you can go from here and you can here. So this is the path from A to D, A to B, B to D. So this is one of the paths. Of course, you may ask a question. So why not A to B, B to E, E to D? That is also another path. So you can write A to B, B to E, E to D. This way also you can write. See, this is also another path. So that means from starting to ending, if you want to reach, there may be multiple paths. There may be multiple paths. Just like in a city, if you want to roam from one place to another place, there will be many routes. There will be many paths. So here also you can represent that way. A simple path. A path P is said to be simple if all nodes are distinct with the exception that V0 may be equal to Vn. A cycle is closed in a simple path. A cycle is a closed simple path. Whenever starting and ending are same, then that become a cyclic path. For example, A to B from C, again C to A. That means A, B, C, A to B, B to C and C to A. Then ultimately a cyclic path. Cyclic path. Connected graph. A graph is one in which some path exists between every two vertices U and V. There are no isolated nodes in a connected graph. In a connected graph, there is no isolation at all. So these are the different terminologies you should know. One is degree of vertex, that tells about from a node how many nodes are connected, and path tells about in which way you have to traverse to reach the destination, and cycle path says starting point and ending point are same, and connected graph means where all nodes are connected each other. A complete graph is one in which every node is connected with all other nodes. A complete graph contains n into n minus 2 by 2 edges. So from a single point, see, this is one starting, this is one node, this is another node, this is another node. From every node you will find the connectivity. So whenever there is a connectivity from one node to all nodes, then that is called complete graph. And there is something called weighted graph. Weighted graph means you will find the weight. That means the distance between the nodes 1 and 2, 2 and 3, 3 and 4, 4 and 5 like this. So here the weight is 1 to 2 is 1, 1 to 0 is 3, 1 to 3 is 4 and 2 to 3 is 2 like this. So you can find the distance between the two nodes, that is called weight. So generally that is represented by positive value. Similarly, digraph. Digraph is known as directed graph. A digraph is called directed graph in which each edge of the graph is associated with some direction and traversing can be done in specified direction only. So you can specify in a particular direction. Loop. Another concept is called loop. An edge that is associated with a similar endpoints. Similar endpoints are called loop. That means starting point and ending point pointing to same place, that is loop. Adjacent node. If nodes U and V are connected via edge E, then nodes U and V are called neighbors. Here one is neighbor of 0 as well as one is neighbor of 2. So that means if you consider 1 and 2, they are the edges. So they are the neighboring nodes. So edge always connect between two neighbor nodes. So these are the terminology you should know for graph. Degree of the node. A degree of node is number of edges that are connected with what? A node. A node with degree 0 is called isolated node. For a directed graph, degree of node is represented in degree and out degree. In degree and out degree. In degree says how many nodes are coming in. Out degree says how many nodes are going out. A node U is called a source if a positive out degree but 0 in degree, that is source. A sink, a node U is called sink if 0 out degree then and but a positive in degree, this is called sink. So you should know what is source and what is sink. Sink means where it is reaching. Source means where it is starting. So they are the terminology you should know. And there are different types of graph. First one is simple graph. Next is multi-graph. Next is complete graph. Okay. A graph is said to be a simple graph if G has no parallel edges. A simple graph G may have loop but no parallel edges. If there is no loop and no parallel edges, then that is simple graph. A graph that has self loop or parallel edges, then or both is called multi-graph. That means see, here it is a multi-graph because between two nodes you are having two edges. This is the node A, this is the node B. For node A and B, you are finding two edges. This is the edge E1, this is the edge E2. Then it is multi-graph. Similarly, please observe here, graph with loop. Graph with loop. So this is also one multi-graph. A simple graph, there is no loop, there is no parallel edge. Okay. Please observe here. Here starting point here as well as ending point here. This is called loop. Whenever starting point and ending point are both the same, then that is a loop. So it is not a simple graph, it is a multi-graph. Similarly, multiple edges from source A to destination B, you are finding two edges. So it is also a multi-graph. So like this you can define. Directed graph means when you find direction. So these are the different categories of graphs. Similarly, complete graph. A graph G should be complete if every node U in G is adjacent to every other node G. That means it is complete one. It is completely connected to all the nodes. So they are the different types of graphs. So you can see even the other examples also. This is a simple graph and this is digraph. Digraph means directed graph. So remember DI means directed. From the name itself you are guessing it is a directed graph. Similarly, multi-graph. Multi-graph means there will be multiple edges or there will be a loop. Whenever there is a loop or multiple edges between the two nodes, then that is multi-graph. It is a simple graph. When there is a self loop or parallel edges, then that is multi-graph. When there is no such things, no loop or no parallel edges, then that is a simple graph. This is multi-graph because there is a loop. As well, there is a edges, multiple edges between two nodes. This is a connected but non-simple graph. It is a connected but non-simple graph. This is a disconnected but simple graph. disconnected. Two graphs are separate each other. You can represent the graph by different ways. One is sequential representation. Second is linked representation. Okay. A sequential representation. In sequential representation, we use adjacency matrix. Adjacency matrix to store the mapping represented by vertices and edges. So, to represent a graph, you can use adjacency matrix. So, adjacency matrix is the main data structure to store the details about the graph. So, in exam, they may ask a question: what are the different mechanisms are there to represent the graph? One is adjacency matrix, second one is adjacency list. So, first mechanism is adjacency matrix. The name indicates matrix. Matrix means it is a two-dimensional array. So, in a sequential representation, we use adjacency matrix to store mapping represented by vertices and edges. So, which nodes are connected to each other? All the details you have to store in a adjacency matrix. So, in adjacency matrix, the rows and columns represented by graph vertices. A graph having n vertices and will have dimension n by n. If there are n number of vertices, then the dimension will be n by n. An entry m of ij in the adjacency matrix represents an undirected graph G will be 1 if there exists an edge between U and U. An undirected graph, the adjacency matrix is represented by shown in the following figure. Please observe here. This is the undirected graph. Now A is one node, B is another node, C is another node, D is another node. Now the graph having 5 nodes and they are connected to each other. This is direction is not mentioned here, so it is undirected graph. Now same graph, how to represent? Using adjacency matrix. And how many vertices are here? Number of vertices are 5. If there are 5 vertices, the dimension of the adjacency matrix should be 5 by 5. Please remember, if there are 4, then that should be 4 by 4. If there are 10, that should be 10 by 10. So the dimension of adjacency matrix depends upon number of nodes of the graph. So here 5 by 5. So there are 5 nodes A, B, C, D, E. Here also 5 A, B, C, D, E. Now if there is a connectivity exists between A and A, then write 1. But here please observe here A to A there is no connectivity. So write 0. A to B there is a connection. So put 1. A to C there is no connection. So 0. A to D there is a connectivity exists. So write here 1. A to E there is no direct connectivity. If there is no direct connectivity, write 0. Similarly B to A there is a connectivity. So write 1. B to B there is no direct connectivity. So write here 0. B to C connectivity exists. Write 1. B to D write 1. B to E there is no direct connectivity. So write 0. So like this you can represent. If you see for example E to A is not there. E is here, A is here. So there is no direct connectivity. So write 0. When there is no direct connectivity, write 0. Similarly E to B also there is no direct connectivity. So write 0. E to C there is a connectivity exists. So write 1. E to D connectivity exists. Write 1. E to E there is no direct connectivity. So write 0. Okay. So this way you are able to represent the matrix. Sorry, you are able to represent the graph using adjacency matrix. So remember, the adjacency matrix is also known as a Boolean matrix. Also known as Boolean matrix because the values are only zeros and ones. 0 indicates no connectivity between the nodes. 1 indicates there is a connectivity exists between two nodes. So this will be maybe source, this will be destination. Source and destination. A directed graph also you can represent through adjacency matrix. So while representing a directed graph, you must be very careful how the nodes are connected, whether A to B or B to A. If A to B are connected, then wherever A and B are there, you must be very careful. A to B you should put 1, but B to A you should put 0. So a directed graph and its adjacency matrix representation is shown in the weighted directed graph. Weighted directed graph, that means there will be a distance as well as there will be direction. That is called weighted directed graph with adjacency matrix shown in the figure below. So please observe here A, B, C, D, E. A to B is there, but B to A is not there. Similarly here, B to C is there, but C to B is not there. B to D is there. Similarly, E to D is there. Similarly, C to E is like this. Various edges exist. Now, same thing you are representing through adjacency matrix. A to A not exist, so write 0. A to B, there is a node exists, so write here 1. So this is the source and this is the destination. This is source and there. A to C, there is no direct connectivity, so write 0. A to D, there is no connectivity, so write 0. A to E, there is no connectivity, so 0. So that means if you observe from A, you can go to only B, because there is only one. Similarly, B to A is not there, so 0. B to B is not there, 0. B to C, there is a node exists, so write here 1. B to D, there is a node exists, so 1. B to E, node doesn't exist, so 0. Like this, you can represent. So like this, you can represent the directed graph using adjacency matrix. Similarly, you observe here weighted graph. In a weighted directed graph, you have to, instead of writing zeros and ones, it is not a Boolean matrix, it is a numerical matrix. So you have to write the weight. Instead of 1, you have to write the value. Now for example, here A to B, so 4 you should write. Earlier you should write 1, now you write 4, because you write the weight. Similarly, A to D, there is no direction specified, so 0. A to E, there is no sense, so 0. Now, for example, 10 I will ask. 10 is what? It is a connection from E to D, so that means E to D, so 10. So, wherever there is a edge exists, you have to write the weight of the edge. So, this is a way of representing adjacency matrix for directed graph as well as weighted directed graph. So in the weighted directed graph, you would write the weight, whereas in the case of directed graph, you would write the either 1 or 0. If there is a connection exists, write 1. If there is no connection, write 0. Whereas here in the weighted directed graph, you would write the value of the edge. If there is no connectivity, write 0. So this is the way the adjacency matrix are used. Similarly, this graph also you can represent to adjacency list, also called linked representation. In linked representation, an adjacency list is used to store the graph into the computer's memory. Consider an undirected graph shown in the figure below. Check the adjacency list represent. Now, here A, B, C, D, E. How many are there? 5 vertices are there. So, to represent this graph using adjacency list, you have to write first all vertices exist. From A, whatever the nodes are connected. Now A to B, there is a connectivity, as well as A to D also there is a connectivity. So it says that A is connected with B as well as A is connected with D. The meaning. Similarly, B. Now here B is connected to A, B is connected with the C, B is also connected with D. So B is connected with A, B is connected with D, B is connected with C also. So this indicates that B is having 3 directions but 3 links. So this is the linked representation. Similarly, C is linked with B, C is linked with E. So you will find C linked with B as well as C linked with E. Similarly, D is linked with A, D is linked with E, D is linked with A as well as D is linked with B. Don't assume that A is linked with B. There is no such concept. So because you are finding they are the source nodes, they are the linked nodes. Next, E is linked with C, E is linked with C as well as E is linked with D. So E is linked with D as well as E is linked with C. Of course, you may ask a question, why not C, D? E with the CD you can write or DC you can write. Both are correct. But these are the different way of representing the graph. Okay. Similarly, for a directed graph also you can write. For a directed graph, you must be very careful in which way directed. Now, A is connected with B only. There is connectivity exists between A and B. Now, when you come to B, B is connected with the D, B is connected with the C. B is connected with the C as a B is connected with the D. Okay. Similarly, C is connected with the E and D is connected with the A. Similarly, E is connected with the D. So, wherever direction is there, those nodes you would write in the adjacency list. So, remember, the graph can be represented by two things. One is adjacency matrix, second one is adjacency list. So, in the adjacency list, there are two parts. One is the set of vertices, and second one is the nodes which are connected to the vertex, that you would write through a linked list. So, each one is one linked list. That's why it is called linked representation. That's why it is called linked representation. Okay. So, you can write the matrices like this. If a graph G with n vertices and E edges and no self loop, then an incident matrix is also one of the way. There is another way also called incident matrix. Here it says that whether there is a connectivity exists or not. If A to I means I comma J, either 1 or 0. If there is an edge exists and incident J to Vi, otherwise write 0. Please observe here, A to A. So these are the, because these are all edges, A, B, C. Earlier you used to write only vertices. Row and column both are vertices. Where here in the incident matrix, this side all vertices and this side all edges. They are all edges. They are all vertices. Okay. So whether A is laid or not. So A is laid on A. So write 1. A is laid or B or not. If there is no connectivity, write 0. So here B is this B is edge. This C is edge. Lowercase letters are edges. Lowercase f is edges. Now my A, whether falling on A or not. A is falling on A. So write 1 here. A is linked with G again. A is nothing but linked with G. So A to G is 1. So whichever edge is linked with A, there you write 1. Now if you think about G, now the node G linked with F, I, J. F, I and J. So that means wherever it is linking, to which node it is linking, there you will find G1. If it is not linked, then write 0. So this is the simple way of representing the graph. This is the third way. So totally you will find 3 means way of representing the graph. Adjacency matrix, adjacency list and incident matrix. So in the incident matrix, you are linking vertices with the edges. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.